Hello and welcome to Group 1's presentation video. So before we begin processing the signal, let me show you how to sample the ECG2 signal in both time and frequency domain. So let's run this code line by line, section by section. So the first, this one will just load the signal, and the second one will plot the signal in the frequency domain using this plot syntax. I'm sure you're familiar with that. And this here will discretize. This will sample the signal. As you can see, the output here. If I can make it bigger, there we go. So yeah, this is a sampled ECG2 signal. All right, so that's the time domain. So let's keep to, this is where the DTFT is done, which my friends will get to later in this video. But we want to know how to sample the signal in the frequency domain. So this again plot will plot the signal in the frequency domain. Sorry, in a continuous signal instead of discrete. So if we want it in discrete, we gotta do the stem once again, and that's how you sample the signal in both time and frequency domain. Thank you very much. That's all from me. Let's get to the next part of the videos. Right, so now that we have sampled the ECG2 signal in time domain, we can process it and convert it in the frequency domain using DTFT, or discrete time Fourier transform. And this is the coding for it. You load Y, you make it absolute, and you unwrap it, you get the phase. This is important to get the magnitude and the phase in the frequency domain. So this is where we plot the magnitude and phase separately in the same figure. And the result is as shown. We get the magnitude and the phase. And there we go. We have successfully converted from time domain to frequency domain via DTFT.
Assalamualaikum and greetings. My name is Ahmad Farhan and I'm going to continue the presentation on the explanation of how we apply convolution to filter the noise in ECG signal. So basically we need two input, which is coming from the low pass filter that had been designed using the filter builder design in MATLAB, and we need another input which is coming from the noisy ECG2 signal. So the way on how we can supply the noisy ECG2 signal is to use the load ECG2 in the MATLAB function. So this is the noisy ECG2 signal plot, and this is the impulse response plot, which is developed from the design LPF, and this is the theoretical formula of the impulse response plot, and this is the theoretical formula in order to develop the convolution, and this is the MATLAB function that we use in order to filter the noisy ECG2 signal. So this is the final output, which is the filtered ECG signal plot that use the formula of convolution, yn equals to xn multiplied with hn. So I guess that's all from me. Thank you very much.
One, two, three. Next, let's look into FIR filter, where windowing method has been implemented for the filter design. A low-pass filter is designed using the filter designer, where the passband frequency is set to be 0.4 and the stop band frequency is set to be 0.45, where both of the values are obtained via trial and error method. In order to filter the noise in the ECG signal, convolution is done, where two inputs are obtained. First would be the impulse response, and the figure is showing the impulse response plot. And the impulse response is convolved with the noisy ECG signal. And upon convolving, a filtered ECG signal plot will be obtained, where the whole process can be summarized into a short coding, which is filter bracket LPF, which stands for the low pass filter, and ECG2 will be standing for the original ECG2. So what it does, where the filter will be doing convolution in order to filter the ECG signal. Next, let us look into the Z transform. The figure is showing the pole zero plot of the low pass filter design. Whereas when the filter is done of DTFT, we are able to obtain both magnitude plot and phase plot. Figure is showing the magnitude plot of the filter, and the figure is showing the phase plot of the filter.
Assalamualaikum and hi everyone. I'm Ifa Atira and I will explain about IIR filter. So this IIR filter is using bilinear transformation technique. The coding that I use is butter bracket 6 0.25 low bracket. Butter is the syntax for the butterworth filter. 6 is the order of low pass digital filter. 0.25 is the value of normalized cut-off frequency. And low is for filter type. And here, the graphical representation of 6 order low pass digital filter and graph of frequency domain plot. Next, here the result of ECG2 signal after filtered using IIR filter, which it show less noise and approximately same with the result of FIR filter. Next, for analyzing IR filter, I'm using syntax Z-plane bracket PA to plot poles and zeros. And here, the result of poles and zeros of IIR filter. Next, for DTFT, I'm using syntax FV tool bracket PA to plot the magnitude and phase response of IR filter. And here, the graphical presentation of magnitude and phase plot of IIR filter. So that's all from me. Thank you.